One of our are pretty good. Pretty good.
Just get 10% of the people who will be present.
All right. So actually, someone asked on Piazza for I think exactly this yesterday, so I'll send them. So I think it's like the first time. Do you guys have access to this if you go to the slides? That's actually kind of cool. Okay, let me.
What?
Yeah, that's
All right. That is actually pretty cool. I think I'm gonna be replaced pretty soon. Okay. All right. Yeah, so as announced on Piazza, there are probably more people than there are here in the room. So there's no new lab today. However, you can go to the lab. The TAs are going to be there. At least today, I did not tell any of the TAs not to show up. I think about 15 people RSVP'd for both the Monday and the Tuesday labs. So if you want to work with a TA one-on-one, you can do that. Or you can just sit there and like try to redo the lab. If you missed a lab, you can make one up. You can get credit for one. I'll check out what's going on today. If the TAs are being underused, I'll let some of the Tuesday TAs go. But today, like all the usual TAs will be there. So what I want to do today is talk just a little bit more about A star, which I think means that I need to review A star from the start because that's probably difficult. And I will then do one more algorithms topic, which I hope I will wrap up today. If not, then Wednesday. And then the 2.5 lectures other than this are going to be AI. The lectures will be on the exam that are coming. I will tell you kind of how to prepare, stuff like that, as we actually cover the material. So please show up, actually, or watch it on YouTube or whatever. Okay. So we are, again, going to briefly talk about A star, just to wrap up the different applications that you can have for A star. So to remind you, what we're talking about is getting through a maze, right? And the way we represented the maze was each square, which is not a wall, would be represented as a node. And then if you can get from this square to this square, then this is represented as a bidirectional edge from here to here. So if you want to get from here to here or something, that's the same problem as walking across this graph. So like somewhere here and getting here. Okay. So one thing that you might like to do is you might like to find the shortest possible path from, for example, here to here. Okay. And one possible way of finding the shortest path is to just run Dijkstra's algorithm. So Dijkstra, and incidentally, so no quiz today, but I was like slightly dismayed when I asked people how to pronounce Dijkstra, and then approximately 15% got it wrong, which means that they just went on the internet at 11 o'clock and clicked a random answer because I told you how to pronounce that. You guys are here, so it's probably none of you. But for the record, it's Dijkstra. So anyways, so one way of going around this is sorry, I got distracted by Dutch pronunciation. But what we're trying to do here is find the shortest path from the source to any destination. So we'd look at this graph. And what we're trying to do is trying to find the shortest path, meaning we want to cross as few edges as possible to get, for example, from here to anywhere else. So the formulation of the Dijkstra algorithm that's actually useful in order to getting to a star is the one with the priority queue. So if you're using the priority queue, what you're doing is essentially you have a queue. So the queue is the nodes that you want to visit, right? And then the priority there is the shortest path from the source to any node that's in the queue. So anytime you put something in the queue, it's because you know that you can get from the source to that vertex in the amount of at the amount of cost that you're also pushing. Make sense? And the way it works is we keep going across the graph. We visit some node, and then we say, okay, if I visit this node, then I know that I can get to this neighbor, and I can get to this neighbor, and I can get to this neighbor at the cost of getting to this node, plus, in this case, 1 for each neighbor, because here, all the edges have the same weight, which is 1. And does that make sense? So that's the strategy. We keep adding nodes that are neighbors to the thing that we just visited. And then from the queue, we get the node with the smallest cost of getting from the source to it. And we proved that that's actually optimal, that we'll find eventually the optimal path. Okay, so we don't need to go over it again. As I said, I'm not going to ask you about the proof, but that's the strategy. So this strategy is guaranteed to eventually get the cheapest path from the source to every node. Yes. Do you need to know? So so the complexity and the proof that it works are separate issues. Certainly, you need to know that if the priority queue has push and pop or DQ on queue of log n, then this is n log n. So you don't need to like memorize it, but certainly like if each operation here is log n and you do it n times, that's n log n. Okay. So like as a matter of logic, you need to know. So okay. So okay, all right. So that's Dijkstra. So Dijkstra is guaranteed to eventually compute the cost of the cheapest path to every node. The problem is that with Dijkstra, you're not prioritizing exploring the nodes that make sense to explore the most. If your goal is to get to the end node as fast as possible, right? Because Dijkstra doesn't know that you're trying to get to the end node. As far as Dijkstra is concerned, what you're doing is you're just exploring, and in whatever order, you're computing the cost of the cheapest path, right? So yes,
So like it goes out in all directions, tries to find the cheapest path.
Yeah. yeah, exactly.
But it doesn't know which one.
It doesn't know which one you want, which means that it might spend time going like in a completely different direction, computing the cost of going there first. Eventually, it'll get to your node as well, but not necessarily right away. Right? So the idea of a star is to just say, well, like, let's prioritize going vaguely in the direction we want. Now, in this kind of graph, you actually kind of know what know what direction you want, in the sense that you can just say, well, like, look at the coordinates of the nodes on the picture, and if the coordinates are nearby, that's a pretty good indication that you're going in the right direction. It might be wrong in any particular case. It might be that the only way to get from this node to this node is to take like the long way around, because everything else is blocked somewhere, right? So it might be wrong, but it's a way of probably getting there. So that's the idea of the heuristic function. The heuristic function in a star is you have some kind of estimate of how promising the node is to explore, and you're prioritizing exploring nodes that seem promising. So specifically, if you have a graph that's just drawn on, a slide or a piece of paper, one indication that a node is promising is that just the Euclidean distance between the coordinates of this node and the coordinates of this node is small, right? And that corresponds to the intuition of, if you're like close as the crow flies to your to here, then that seems promising. Not guaranteed that it's good, because this is pretty close to as the crow flies to this square, but you can't even get from here to here at all, right? But if you prioritize going vaguely in the right direction on the maze, that probably makes sense, right? So that is all that A star does. So it takes the Dijkstra algorithm and just says, instead of prioritizing by just this, so instead of prioritizing by the distance from the source node to the current node, we'll prioritize by this plus how promising the vertex is to explore. Yeah.
If we're like reporting the shortest path, though, we're just still considering the distance.
That's correct. Okay. So that's all that's all it is. So it's a modification of Dijkstra. One way to look at it, at least, is you're modifying Dijkstra, and the order in which you're exploring the nodes is you're prioritizing the nodes such that getting to that node plus an estimate of how far the node is from the end goal is as small as possible. So take away h of v, and this is just Dijkstra. Okay. So, and the goal there eventually is to find the shortest path to the end node as soon as possible, rather than when the algorithm gets around to it. All right. So that's a start. So questions about this? Okay. So I wanted to take a brief moment to talk about other contexts where a star or something like a star might be useful. So this is so we've seen this when we talked about Gamoku in ESC180 briefly. We hadn't had the vocabulary of graphs at that point. So this is what's called the game tree, or like a search graph. So essentially, you can think about chess positions, and then one chess position is connected to another one if there is a valid move that you can make in order to get from here to here, right? If you're trying to just play chess it doesn't really make sense to think about it in terms of graph search problem. If you know like chess puzzles where there is like, 3, 4, 5 moves that make it so that you win, that makes more sense. But you can think about it as games where you are starting from this position, and what you want to do is you want to win as soon as possible. So winning as soon as possible means getting from the start state to an end state where you won as soon as possible. Does that make sense? So in this kind of situation, one possible heuristic would be, well, how good of a position is it? Like if the position for you, like if you play white or whatever, if it seems like things are going bad for white, you probably don't want to prioritize exploring that branch. How do you know whether things look bad or good for white or black? Well, you can just count the pieces, for example. Or if you remember what we did in Gomoku, there's like various things you can do. So in Gomoku, what we did is we like counted up how many sequences of 3, how many sequences of 4 we have, and so on, right? So that's another situation where you can use a heuristic. I kind of wanted to do this, even though in chess you would not use a star to build up an intuition. Really, I want to talk about something relevant to your life. I know how many people play chess, but you also have calculus problems, right? So here's one way. So I kind of like was annoying DeepSeek this morning to come up with this example. But here's one way of thinking about trying to prove something like this, right? And you can say, well, like, I need to prove it. I know how to prove it. There's various things I could try to do to transform this inequality in order to get to something where I can just say QED. The way I set it up is that the easiest way to do it probably is what's called completing the square. I know how many people know about completing the square? Okay, most people. Anyway, if you don't, like, this is it. It's like making it so that there is a square expression inside there, right? And here, like, you can just say, well, like, like if you just make this like x plus 1 squared plus 1, which it is, then this whole thing is greater or equal than 0 because the square is greater than or equal to 0 and 1 is greater than 0. So the sum is greater or equal than 0, right? So that's like an easy proof. You can also imagine, well, like maybe I know what I'm going to do. Maybe I'll factor it or something. And I had to come up with something that doesn't work. So obviously, like, you can't factor a polynomial that's always positive, doesn't have any roots. So not going to work, right? And you can imagine, like, you look at this inequality, you try to prove it, you don't know what to do. There's various things you can do. And you can imagine just thinking, okay, like, I'll just think about it as a graph where an edge is a valid transformation, right? So if you like regroup things and then like you say x squared plus 2x plus 1 is equal to x plus 1 squared, that's like a valid transformation. So that would be an edge. And nodes would be like states of the transformed inequality, right? And there's different strategies that you can use that actually do correspond to algorithms that we've seen in our course, right? So you can imagine saying, I'm going to do depth first search on this kind of thing. What does it mean? It means that you try something, and that's clearly not the solution yet, but you're going to just like pursue it further and further and further until either you get nowhere or you get to say QED. Right? And then you'll try another branch, and then you'll try another branch. So that would be depth first search, right? So like going, here and then here, 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 here until, okay, you're stuck, and then maybe you'll explore this. You can imagine doing like breadth first search as well. That doesn't make as much sense. So to say, well, I'll try like every possible small step and see where it goes. Nobody would do that. What you probably want to do and what you probably do is actually something that's a little bit like A star, right? So A star, of course, is about finding the cheapest path, not just any path, right? And you usually don't care. Like if you find a solution that's like not as elegant as it might have been, that's so has more transformations than necessary, that's probably fine. But you can still think about it as what you would do is you would say, well, like I'll try to go to this node and I'll try some kind of heuristic function, which you have in your mind, right? Like you look at something and you can tell, like, is it promising or is it not promising? And if it's promising, then I'll prioritize it. If it seems not promising, meaning that it seems very far away from a QED, then maybe I'll abandon it. Make sense? So that is essentially a star. Now, to formalize it, I think kind of you all kind of develop an intuition for what seems promising and what seems not promising algebraically. If you really want to formalize it, I think what you would probably say is like, does it seem very long or does it seem very short? In part because if it seems quite short, then probably you can get to be able to using a theorem or something for it, right? If it seems like it's a huge expression and it just keeps growing and growing and growing, probably a proof is not going to come out of it. So not guaranteed, of course. Sometimes you need to expand only to then regroup the terms and do something with them. But that's a heuristic that you can use. Does that kind of make sense? So it's supposed to be more like vibes than anything else. It's not like a formal algorithm. Because like in order to get the transformations, you would need to actually like encode the equation somehow. We have not done it in Python, and then have like rules about how you can transform the expression. That's kind of hard. But you know, like if you're stuck on the calc exam, think a star. Maybe it'll help. Okay. Question. People seem to doubt me. Yes. If you the question was, if you say a star is for Professor Gerjoy on the calc exam, how much trouble are you in? Like I'm friends with Jim Davis, so it's probably going to be okay. But it really depends on what you put on the answers to the other questions. So make sure that the other ones are not like that. I think you can do it on one question. All right. Okay. Other requests for calculus exam strategies? Anything? Okay. All right. So last topic. Binary search trees. It's not going to be very long. I decided to kind of cut some of the material this year. So I do, however, want to give you an idea of how you could basically implement Python completely. And we've almost done everything. So we've done the memory model. We've done lists. In fact, probably everyone is tired of doing lists. But we haven't done sets and we haven't done dictionaries. So I want to do that now. So of course, I think it's not that difficult to implement a dictionary that's kind of slow, but it's hard to implement a dictionary that's fast. And that's what we're going to do now. So that's what we're going to do. But we'll start with sets. So the set abstract data structure allows for insertion, it allows for deletion, and it allows you to ask whether the element is in the set. So that's what I want to implement. So to be clear, doing this slowly is very easy. So you'll just say, so I'll name it my set. And I'll say self data is just the empty list initially, right? And then if I wanted to insert, I'll just check if it's already there. And if it's not, I'll just append it. And so you can do the contains if you want to do the in operator, but I'll just name it is in. So like something like this. So essentially I'm just like wrapping a list inside my set, right? That's all it is. The problem is that it's kind of slow, right? So insertion is going to be on. If I implement deletion, that's also going to be on. And search, meaning it's in, is also going to be O of n here, right? Because the way it has to work inside is like if you want to know whether the element is in the list, you have to go through every element in the list. Does that make sense? So what I want to do is do something that's faster than this. Okay, does the task make sense? So, okay, so here's what you can do. Sorry, so one more thing, just to be clear. So map, so this is called map in general. In Python, those are called dictionaries. Those are basically like sets. It's not really different, right? Because what you can do is instead of so this is going to be the same, and then here this is going to be x and value. And here I'm going to append x value like this, and then is in is going to be, you know, so for x value, and then get would be just go through all of them and retrieve them. So I hope that you don't really need to type it in because it's kind of clear what's going on, right? Does that make sense? And that's the same as set essentially, right? It's just that in addition to just having keys, I have values that are attached to the keys. Is that making sense to everyone? Questions? This one. So this is so here like data looks like this, right? So it's like key values. So it's like it would look like ESC190 A plus, and then ESC195 D minus, and so on, right? You wish. So something like this, right? And then when I say for k comma value and self the data, it's going to be like k is ESC190, value is A plus, and then k is ESC195, value D minus. Yeah. Exactly. Yeah. And that's what I'm doing here, right? So like when I'm inserting, I'm saying append the tuple x comma value. All right. So, and this is again going to be O of n, right? Because in order to get the value, what you want to do is you want to look through the entire list of tuples and check whether the key matches any one of the keys in there. right? Does that, so this is also open. Okay, so it's easy to do if what you want is just something open. It's harder to do if you want something that's faster. So here's a way to do it faster. So that's called a binary search tree. So the way the tree works, so the terminology here is, so the tree is kind of inverted. So this is called the root sometimes, and then those are called children ordinarily. In the binary search, so it's a graph, it's a directed graph, and then the root has children, the children have grandchildren, and so on. So in the binary search tree specifically, all the descendants on the left, so meaning the left child and then the left and the right child of the left child and so on, they're all smaller than the root. And then everything on the right is larger than the root. So that is what the binary search tree is. So it's a graph specifically with a root and up to two children for each node. Does that make sense? So, okay. And why this all makes sense together is going to be apparent soon. So let's say that we want to know whether an element is in the tree. So let's say we're looking for 4. So the rule is everything on the left is smaller, everything on the right is larger. So that means that if you start here, you're definitely looking to the left if you're looking for 4. And then here you're at 3, so you definitely want to go right. And then you're looking for 4, smaller than 6, so you definitely want to go left, and here you are. Does that make sense? So, okay. So what's the complexity of this? So it depends on the tree, right? So the height of the tree refers to the longest path from the root up until the end. Okay, so in this case, the height is 1, 2, 3. And that is as many steps as you would need in order to get to the thing that you're looking for, if it's there at all, right? Just by definition, like the longest path that you can take, which is the height, is as many steps as you could possibly take. Does that make sense? It's like I'm saying the same thing 2 ways. So the question now is, what could the height be? And the answer is, it's kind of complicated. So in the worst case, the height is just the number of elements minus 1, because this kind of tree does obey the rule, right? So the rule is only everything on the right is larger, everything on the left is smaller. So here, everything on the right is always larger, so that's a binary search tree. And the height of this is n minus 1. It's as many nodes as there are minus 1, because there's like 1 fewer edges than nodes, right? So in the worst case, the lookup is going to be O(n), where n is the number of nodes. However, there are ways to make it so that which you can read about, but you won't hear about in this course, there are ways to make insert and delete be such that the tree is almost complete. And if that is the case, so complete just means basically everything has two children. And if that is the case, then the lookup is going to be O of n. So I'm going to briefly make this argument. So imagine that the tree looks kind of like this. That is going to be on YouTube. You don't need to copy the exact numbers. So how many nodes are there? The answer is 1 plus 2 plus 4. So specifically 2 to the 3 minus 1, which is 7. So in general, does that make sense? So if it's like 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3 and so on, then the number of nodes is going to be 2 to the h minus 1. So done this kind of thing several times in 180 as well, right? So that means that h is approximately log n. Because just take the log of both sides. And remember that h is the search, meaning find whether the node is there, is O of log n. And note that this looks like a representation of a set, right? So if you arrange the numbers in this way, then you can look up whether a particular number is in there in O of log n time. Does that make sense? So here we just have keys, but you could imagine also attaching values there. In which case you can have a dictionary with, again, O of log n lookup time. Does that make sense? So I'm not going to implement this fully because implementing this fully requires being able to insert so that the tree doesn't become the straight line where the lookup is O of log n. And that's extremely, extremely annoying to do, sorry to say. However, looking up, so like if this is if the tree is already arranged like this, then looking it up is not that hard. So that I do want to show you. So here's how you can make a tree, right? So this is going to be like a graph, except with a graph, we had a list of neighbors. With the tree, we just have 2 children, right? So left, possibly right. Or right, possibly left, right? So we'll have a node, and then in order to make a tree, so if we want to make a tree that's like kind of like this, then we can create the node with data 3, and then can have like a left child, we can have a right child. And then in this case, the left child is going to have both a left child that's 0 and a right child that's 2. Make sense? Is that good? So, okay. So if this is how the tree is defined, then here's one way to look up whether an element is in the tree or not, right? So how do we think about this? If I look at the tree here and I want to know whether 4 is in the tree or not. Well, the only way that 4 is going to be in the tree is if the 4 is somewhere here, right? So if we think about it recursively, 4 is in the whole tree if 4 is in this subtree over here, right? If not, then not. If I want to ask whether 15 is in the tree, then the only way that 15 would be in the tree, it would be on the right. So I'll return true if 15 is in this part of the tree, and false if it's not. So that's the idea of this recursive implementation, right? So I'm just going to say, okay, like here's the root and here's the element I'm looking for. And I'm going to say, if they're there, that means that we haven't found the element. If the root is exact, if the value is actually matching at the root, we return true. And then we'll look in the right subtree if the element must be on the right. We'll look in the left subtree if the element must be on the left. And we'll just return whatever this is returning if the value if the value is smaller than the element, because if the element is there at all, it's in the right subtree. If it's not there, then we should return false. Does that make sense? So, okay, so that means that if you build a tree like that, and if you make it so that it's approximately balanced, that's going to be all then lookup. We are not going to do insertion. So I want to do just this, but with a dictionary. So this is going. So this is the tree. So in order to make it a dictionary, what I'll do is I'll have keys and I'll also have values, right? So I'll call this Alice. And I'll call this Bob. This is going to be Charlie. So this is a tuple now, right? And this is going to be Dave. And this is going to be Eve, sure. All right. So the tree is now going to look like this. So this is like 3 and Alice. And this is now like 1 Bob. Wait, isn't it? It's going to be 2 Bob, I guess. And this is going to be 5 Charlie. And this is Dave, and this is, so sure why they're repeating here. So this is 3. Oh, 2.5. It must be 2.5, I guess. So that is now like this. And now let's say that I want to do something like a dictionary. So I want to get zero is Dave 0. Oh, Dave is 0 now. Sorry. So left left, right, okay, and Dave, yes, it should be, yes, thank you. Okay. So what I want to do is I want to get, and this is going to be root. So I want to get the name that corresponds to the key. And assume that root is the root of a binary search tree. So it's the same algorithm, right? So I'm going to say, okay, so if root is none, then I haven't found it. If the key is already there, then I'll return the name that corresponds to it. And then if it's smaller, then I'll look on the left. If it's larger, I'll look on the right. So if key is smaller than root val 0, so if I'm here, but I'm looking for a 2, or I'm looking for a 0, I'm looking for 2.5, I'll just look at this subtree, which is rooted here, right? And otherwise, I'll look on the right. Okay, so it's the same thing, except I store those tuples so that instead of just saying the key is there, the key is not there, the way I would with a set, what I do is I look up the node, and in that node, I get the value, and I get the string rather than just the key. All right. So what we've seen here is a way to implement dictionaries with O of log n time. So that's assuming that you can get a balanced binary search tree. So you have to organize the keys in a clever way rather than in just an arbitrary way. There is a way to do it. It's quite annoying. If you're in Robo, you will take CSC 263, where they will teach you about that. Otherwise, just look up AVL trees or red-black trees, and they will tell you how to do it. I'm not going to torture you with it. I don't like the topic. That's it. And that's about everything that you need to know in order to, in principle, be able to implement everything that's available to you in Python and C, right? So we've seen how to do strings, we've seen how to do objects, we've seen how to do lists, and now we've seen how to do dictionaries and sets. Python, actually, the actual Python uses a different mechanism in order to do fast dictionaries. It uses something called hash maps. Java, however, by default does use this mechanism in order to do something on dictionaries. So that's everything I have to say about that. We'll start AI on Wednesday. Please come. It's going to be on the exam. Okay. All right. See ya. Bye.
No, I mean, I read it. And I make